Good. So we have a test in less than 2 weeks. It's on the 19th, but we are a little behind. I hope that we can start 11:3 today. We'll see how it goes. So if you have any questions on the homework, please email me. And hopefully you're staying up with this homework. It's some of the sections don't have a lot of problems, but a lot of the problems are time consuming. So try to keep up with it if you can. We left off in 11.1 talking about our Taylor polynomial, and we use that to approximate e to the x. So remember, the general term for the Taylor polynomial is the nth derivative evaluated at a, and a is just the center where we're choosing to construct our polynomial. Nth derivative at a over n factorial x minus a to the nth power. So if you can just remember that general term, all of these terms actually fit that format. And what we came up with for e to the x was, so we found its fourth order by finding the fourth derivative, evaluating the function all the way down to its fourth derivative. And again, those are going to be the numerators of each term in our polynomial that's approximating e to the x. So that's just the numerator, then we have to divide by n factorial and multiply by x minus a to the same power. And what we ended up with was this polynomial here, 1 plus x squared over 2 factorial, etc. And mentioned that we could use this to approximate e to the x for values near x. It's not, unless we look at a graph, it's not really clear what we mean by near. And it also depends on what level of accuracy you need as well. So we did use that approximation to approximate e to the 0.1 and saw that it was very accurate to the actual value here at the bottom. Does anyone have any questions on what we're doing there? Okay, so yes, the other question we have here is, make a split here. Use our fourth degree Taylor polynomial to approximate e to the 2.5. So this, remember, we were approximating e to the x. When we say approximate e to the 2.5, this now is our x value. So we're going to say p sub 4 of 2.5 is 1 plus x squared over 2 factorial, x cubed over 3 factorial, and x to the 4th over 4 factorial. So I mean, like to a calculator, it probably makes a world of a difference evaluating polynomials or powers versus exponential or logarithmic type functions. Maybe to us it's kind of a moot point, but we certainly know how to square and cube and stuff like that a lot easier than we can multiply e by itself 2.5 times, right? I mean, how would you do that by hand? So the purpose of this here is just to illustrate something that we want to address or talk about. And this value, do this, come out to be 10.8567, 7083. For p sub 4 for the approximation. But the actual value of e to the 2.5 is 12.18. 249. So with that first approximation, what was it? 1, 2, 3, 4, 5, 6. So it was off in 10 to the negative 7th place, but this one's not even accurate. You know, it's just really bad in comparison. So why is this approximation so much worse? So why is P sub 4 of 2.5 a bad approximation of e to the 2.5?
You lose accuracy as it gets bigger?
Say that again?
Said you lose accuracy as the number that you're going to gets bigger?
Gets bigger in the sense of away from zero, away from the center. Yeah, so remember we centered this fourth degree polynomial at 0. So in other words, the line, the parabola, the cubic, the fourth degree, they were all built around that point. So 2.5 isn't, you know, quote unquote near 0. So we'll just say that since 2.5 is not near 0, which was our center. That's pretty much why it was off.
What constitutes near?
Do what? Yeah, we don't know. It's ambiguous. There is an error bound on the using Taylor polynomials. We don't really do much with it. We can talk about, you know, like if I use this fourth degree polynomial to approximate e to some value, how much would I be off? But that's about as good as we can get with, right now anyways, we can just say near. So how could we fix this? Do what? Yeah, we can move our center. So to fix this, we have a better approximation of e to the 2.5. We can actually do two things. One is to move the center. Closer to 2.5. It doesn't have to be right at 2.5. Could be a number. And if you think about, like, the whole purpose of the polynomial is to approximate e to the 2.5, but if you try to come up with a Taylor polynomial centered at 2.5, then it's kind of a moot point because you've got to evaluate its derivatives at 2.5, and all of the derivatives are already e to the x, right? So if you could evaluate e to the 2.5, there wouldn't be any reason to center it at 2.5. You might see, like, the natural log of some number that's really close to 2.5 and center it there so you can calculate e to that value really easily. But the point is, moving the center closer to the value of x that we're trying to approximate would fix that. And the other thing we could do is actually, and this one won't always work, but we could add more terms. We only went out to the 4th degree, so we could go out to like the 12th degree or the 15th degree. And I'll just say, for example, we could find P sub 15 of x. But this does not always work. And so as we go forward with chapter 11, we'll see that it actually depends on the what we're going to call the interval of convergence. And I'll just put that here, so if you reference it later, you'll know what we're talking about. It depends on the interval of convergence. Some functions, power series that we look at, converge for every value of x, so no matter what value of x you put in to the series, it will always converge to that function. Some power series, however, have a very limited window in which they converge to a function. So for e to the x, we'll see, I think in the next section, that the power series for e to the x, or the Taylor series for e to the x, converges for all values of x. And so here was our approximation in blue. Using that approximation to approximate E, which is in red, and we really can't see any difference. I mean, the difference was 10 to the negative 7. So now we get closer, we can actually see that, yeah, there's a difference between the polynomial in blue and the actual function in red. Okay. And that difference was 10 to the negative 7. If we use that to approximate at 2.5, I mean, we're looking at, what is this, 1, 2, 3? Yeah, this is, each grid is 1 by 1. So we're at a 1-to-1 scale. We can already see the difference between the approximation and the polynomial. So the actual value was 12.182, whatever, and this value was something 10, wasn't it? Well, it's way down here, but anyways. Way down here. Put it right there. But if we add more terms to that blue curve, we get a different polynomial, but we get a better approximation over here specifically. So here's the 7th order, or 7th degree Taylor polynomial. You can already see that's much better. Here's the 11th degree, even better. So you see it actually converges pretty quickly. 15th degree, even better. So now it's pretty accurate all the way through, just using 11th degree polynomial. But also notice what happens over here as we keep increasing. So now that 42 degree polynomial that has powers all the way up to x to the 42 power is now a pretty good approximation for e to the x for an even larger interval, right? This is like negative 18 all the way to, you know, who knows where on this one. You know, now we're pretty good around even to negative 20. But so as we go through various types of functions and series, we'll see that it's not always the case where the polynomial just keeps getting closer and closer to the actual function. Outside a certain domain, if you will, the polynomial will look nothing like the function. But like in a certain window, they'll look exactly the same, and that's our interval of convergence. Do you have any questions on that? So that's for the e to the x in the polynomial we just plotted. So approximate cosine of 0.1 using a 6th order Taylor polynomial centered at 0. Do y'all remember if cosine was a even function, an odd function, or neither? Even, cosine's an even function. So what would we expect when we looked at the Taylor polynomial for cosine?
It alternates terms.
It alternates terms, yeah. I mean, we might suspect that from the derivative, right? Negative sign, and then it's down the line, it's positive sign, positive cosine.
Like there's a term that exists, and the next one is just multiplied by zero.
By zero,
and then the
right.
next term exists.
But what kind of powers would we expect in a polynomial?
Is it 1, 3?
Those are odd numbers, though.
That's sign, okay.
Yeah.
So it's 2, 4.
Yeah, even, like, we would just see even powers on our polynomial, because cosine is an even function, right? We wouldn't expect cosine, since it's an even function, to ever be well approximated by an odd polynomial, right? Okay, so what we really want to do is we want to come up with a Taylor polynomial for cosine of x in terms of x first, and then we'll worry about plugging in point 1, centered at a equals to 0. And remember the general term here, the nth derivative evaluated at a, or 0, excuse me, over n factorial times x minus a to the power of n. So we have our function. We need to evaluate that at the center as well. And then we need to find the, all the way up to the 6th derivative, because we're after the 6th order polynomial. First derivative, negative sign. Second derivative, negative cosine. Third. Fourth. Fifth. And the 6th. So then we need to evaluate all of our derivatives at the center at a equals 0. So we have f of 0 is the cosine of 0. F1, f prime of 0 is negative sine of 0. F double prime of 0, negative cosine of 0. Triple prime at 0, 4th derivative at 0, 5th derivative, 6th derivative. So our terms with the 1st, the 3rd, the 5th power, those are all missing because their coefficients are just 0. 0 times all of that gets rid of it. And then we also see that they're alternating. You have positive 1, negative 1, positive 1, negative 1. And so remember, these numbers here are just these numbers here. You still have to put them over the corresponding factorial and x minus a to the same power. So 1, 0. I think we'll have to scoot down here and write it. So the 6th order polynomial that approximates cosine near x equals to 0, what would that look like? What would our first term be? 1. Yeah, your first term is always f of a rather. So our first term is 1. Our second term would be Do what?
X.
So we have to do the coefficient here. The next term is this coefficient 0 over 1 factorial times x minus 0 to the first power, right? So let me do this. Okay, our second or third term rather, coming from the second derivative, coefficient of -1. That's coming from the second derivative, so it'll be over, excuse me, over 2 factorial times x minus a, which is 0, so x minus 0 to the same power to the second power. Let's see if it's confusing. Our next term would be what? 0. And that's coming from the third derivative, so let's just write it out so we're just getting accustomed to the pattern. 0 over third derivative, 3 factorial x cubed. Next term, coming from the fourth derivative, over 4 factorial times x minus 0 to the fourth. That coefficient was 1. I'll just have to start here. The next term coming from the fifth derivative, over 5 factorial x to the fifth, coefficient there is 0. And the sixth term, coefficient -1 over 6 factorial x to the sixth. So the order, whatever the nth order Taylor polynomial, you have to work down all the way to the nth derivative and put all of those coefficients in. So does everybody agree that's a sixth order polynomial? The terms, there's not going to be 6 terms or 7 terms because some of these cancel, but go away rather. So we just have 1 minus 1 over 2 factorial times x squared plus 1 over 4 factorial x to the fourth minus 1 over 6 factorial x to the sixth. So that was for cosine of x near x equals to 0. Again, we can say that this is approximately cosine x. Near x near 0. Does anybody have any questions on that? All right, I'm going to plot this. So let's compute. I'll just have y'all compute the value, the approximation. Approximation and the exact value. Yeah. So y'all compute those, and I'll just plot it.
It's gotta be wrong. Let me do that with the second term. Why did we do .1? Why didn't you do .1? Probably a lot more accurate than recording. Which section?
11.1. It was like, you had like 3 times 10 to the negative 8. It's actually 0.54 times 10 to the negative 8. Because it's subtracting 2 things, so it's just like my calculator rounded
All right, so the approximation was coming from P sub 6 evaluated, what are we plugging in?
0.1.
0.1, we're approximating cosine of 0.1. So P sub 6 of 0.1 is approximately, we'll just write this out at the end, it's approximately cosine of 0.1. And what did you get for P sub 6 of 0.1?
0.99504.165.
That?
Yeah.
What's that? What's next?
4165.
Okay. Yeah, did y'all get that? Okay. And then let's compare that approximation to the actual value. The actual value is what?
The same.
Exactly the same?
Yep.
So how many places is that? 3, 6, 9. So at least we know it's accurate up to 10 to the negative 9. So here's our, here's cosine, here's our polynomial. I don't know how far we want to go out, but we had 1, 2, 3, 4 terms there. So there is our polynomial. And we just see if we add more terms.
By like 20. It's off by like $1 billion.
I mean, it's almost like magic, right? Like that polynomial is like fitting cosine perfectly, the more terms we add. So I don't know how far this will go before it has issues, but, you know, there's the 42-degree polynomial for cosine. Do you have any questions on any of that? All right, well, we have that one last example, but I think we're going to skip it for time purposes. Actually, no, let's go ahead and do this. It's centered at, I think it's the first one in this section that wasn't centered at 0. So this is centered at 1, at a equal 1, and the third order, we only have to find the third derivative. So really the function we want to start with is just the square root function. F of x is the square root of x. And find its first, second, and third derivative. And then evaluate first derivative, second derivative, negative 1/4 x to the negative, I'm going to add 1, no, subtract 1, negative 3/2. Third derivative, 3/8 x to the minus 5/2. So if we tried to center this polynomial at 0, what happens?
You're wrong. It says it's at 1.
Yeah, it says it's at 1, but what if it said center it at 0? What would happen?
You take the square root of 0.
You take the square root of 0, which is 0. You plug it in the first derivative. You can't do that, right? You just got an undefined first derivative, an undefined second derivative, an undefined third derivative. So if we try to center it at 0, the polynomial approximation we come up with is just 0. So that doesn't help out. But at a equals 1, we have f of 1, which is 1. F prime of 1, f double prime at 1, and triple prime at 1. So those are our coefficients. Take 2 minutes and write out the third order Taylor polynomial for this approximation, or the third order Taylor polynomial. Does anyone want to share what they came up with?
Okay, get ready to write.
All right.
1 plus 1 over 1 fractal times x minus 1 in parentheses to the first power,
Okay, to the first. All right.
plus 1/2 over 2 fractal,
1/2 all over.
yes,
Okay, like that. Okay,
that's because I was just plugging this
sure.
in. Times in parentheses x minus 1/2.
X minus.
1/2.
Now remember, this one here is your center. So it's always this term, or the power on x, is it's x minus the center. So just like you had here, it'll still be x minus 1
Okay, so x minus 1 squared
squared. Yep.
plus negative 1/4 all over 3 fractal times x minus 1 to the third.
To the third. What do y'all think? So come up with that? Initially, one more?
Yeah, we have.
Oh yeah, the 3/8. I guess I have to write it down here. As wishful thinking.
Plus 3/8 over 4 fractals. Times x minus 1 to the fourth.
To the 4th. Yep.
Wait.
Okay, yeah, so our coefficients here, I'll make these 1,
Yeah, I'll still one.
our 1/2 should be here.
Yeah.
There should only be 4 terms.
Yeah, there should only be 4 terms.
1 plus.
Remember that 1 corresponds to the 0th derivative, if you will. So that 1 should, if you're attaching it, should be over 0 factorial, which is 1, times x minus 1 to the 0, which is also 1. So this term right here, right, so the first term is 1. Let me get this out of the way. And so the 1/2 over the 2 factorial x minus 1 squared. Is that right? Where should the 1/2 be? Yeah, well, the 1/2 is coming from the first derivative. So let's see if I can scoot this over. Nope. I'm gonna erase this. Coming from the first derivative and the first power there. The 1/4, the negative 1/4 rather should be, so if I can move that. Yeah. Negative 1/4 should be over 2 factorial and x minus 1 to the second. And then this last one here should be our 3/8. That's coming from the third derivative, so it needs to be over 3 factorial. X minus 1 to the third. Okay. So super close, so just I had it shifted. All right, do y'all agree with that? Is that what you all came up with? Anybody get anything different? Maybe see if you did. And so I mean, we could just use that, but I'd rather, this is 1 plus a half times x minus 1. We've got a minus 1/4 over 2, which is a minus 1/8 times x minus 1 squared. And we've got 3/8 over 3. That's, the 3's cancel, and we have over 2. Oops, this is plus. So plus 1 over 16, x minus 1 cubed is p sub 3. Okay, does anybody have any questions on that? And then we want to use that polynomial approximation for root x to approximate the square root of 1.05, thanks. Okay, oops, I need the powers. Okay, so that's the approximation of the square root of 1.05. So p sub 4 at 1.05, 1.02465.
Wait,
313. P sub 3, yeah, I'm sorry. So P sub 3, 1.024695313.
And then you get the determinants 4.
So that's our approximation, the exact value, just so we can see how close we are. Exact value is 1.024695077, and so on.
I got, as the approximation, 95313. And
Do what? Yeah, it's the square root of 1.05. But remember, this polynomial that we're coming up with is approximating the square root of x. So we would just plug the argument 1.05 into our polynomial. You're saying you got a different value, Sean?
no, for the approximation.
For the
exact. Yeah.
Oh, the approximation? Okay.
Oh, I didn't see you had it up there. Never mind. Yeah, that's what I got.
Oh, okay, okay. Let's go check it. Okay, does anyone have any questions on that? Say that again, sorry.
So my approximation is completely different, but I have it set up just like that. Mine came out to be 1.549, blah, blah.
Yeah, probably calculator error then. What kind of calculator are you using? Oh, okay.
I believe you guys, I didn't do any adjustments, just plug it back.
Yeah, well, let's just double check.
Otherwise,
You don't do that unless the buttons are the exact same.
Ever since I saw your Aldecra shirt, I've been saying it's like people random.
Got it?
I feel like there's
the first physics. This thing's being weird, so.
I don't your house.
All right. Bye-bye.
You don't realize how much you need it.
Season 3 was my favorite.
All right. So then what we'll see in the next section, 11.2, is we'll actually start looking at power series and properties of power series. And then 9.3 will take, so in 9.3 we'll take what we do in, in 11.3, we'll take what we did in 11.2 and 11.1 and put that together so we can start looking at functions. So a power series is an infinite series. We'll use, I guess, K. Your infinite series with some coefficient C sub K. Times x minus a to the k. And the C sub k's are the coefficients for power series, the coefficients C sub k in a power series are usually random. Meaning it's not easy or doable at all to come up with a particular pattern for the coefficients. But we should also remind ourselves that in Taylor's polynomial, in Taylor polynomials, that sounds better. In Taylor polynomials, the C sub k, the coefficients, weren't random, right? Each coefficient had a particular, definition, which were the nth derivative evaluated at a all over n factorial. So those aren't random. So when we kind of move back and look at a more general series and say that every Taylor series or every Taylor polynomial in effect is a power series, but not every power series is a Taylor series or a Taylor polynomial. So this is the more generic thing. So in 11.1 is when we look at finite polynomials, which were the Taylor polynomials. Infinite polynomials are looked at in 11.2, 11.3, and 11.4, more or less. And when we have a infinite polynomial with a center at a equals 0, they have a special name called the Maclaurin series. So usually those are actually the most friendly because it's not x minus something squared, x minus something cubed, it's just x squared, x cubed, x to the fourth. Okay. And so the first thing we can actually look at is our geometric series as a power series. If you remember that the sum of infinite sum of r to the kth power 1 plus r squared, etc. What could we say here if the absolute value of r is less than 1? What do we know about the geometric series? It converges, yeah, and what does it converge to? a value, yeah. Very good.
First term over 1 minus r.
Yeah, first term, 1 over 1 minus r. So here's another way we can look at that. We can say then, we don't have to define it as f of x, but it is a function of x. So what if we said instead of looking at r as some fixed number, like 1/3, 1 plus a third squared plus a fourth, right, et cetera, what if we just looked at this as the sum from k equals 0 to infinity of x, a variable, to the power of k? Right, because generically speaking, our geometric series, we just said as long as that ratio is less than, an absolute value is less than 1, then that would converge to 1 over 1 minus r. So the sum of x to the power of k, which is 1 plus x squared plus x cubed, etc., is actually 1 over 1 minus x if the absolute value of x is less than 1. Now, when we, like, what we're actually implying here is that this series converges to this function if you're within that boundary of x. And I think that's really easy to see. It's just a replacement of r, which was some fixed value, with some variable x. But everything else symbolically is exactly the same.
Well, no, it's just 1, 2, 3, 1, 2.
Okay, so here's our function 1 over 1 minus x, and here's the series for that.
And then calc 3 is just different.
So it happened really quickly. Let me scoot this down a little bit. So there's the quadratic, the cubic, fourth degree. Okay, so we see that series is approaching or converging to the function 1 over 1 minus x. Let's see how far this will go out.
Oh, yes. 1,000. He just right.
There it goes. See, that's 1,000 terms. You didn't see much of a change there. So we're saying that outside of the interval, the absolute value of x less than 1 means that x is between 1 and negative 1. And so if we look at anything outside of that particular window, then no longer is this series that function. So here's outside of 1 up in this direction too. You can maybe start to see the difference between.
It never gets outside of
Maybe not. I mean, maybe it's for larger values, but definitely see that on the negative end. Can't really see it here, but anyways, that's outside of the interval of 1. So no longer is that series that function. No longer do you have convergence. Does that make sense? I think that can give us a visual representation of convergence in this sense versus, oh yeah, the series converges, it converges to 1/2 or converges to a third, right? Now we can say this series converges to a function of x for those particular values of x.
That would be less than, that's the interval.
So a power series, as we defined above, this is a more official definition, I guess. We have A and C sub k are real numbers. X is your variable. The C sub k's are your coefficient. A is still the center, just like it was with the Taylor polynomial. The set of values of which X converges is called the interval of convergence. So let's just back up here and say that this function here, or rather this series converges to this function if the absolute value of x is less than 1, or if x is between 1 and -1. So that gives us our interval, right? We have all real numbers, but it's only from -1 to 1 in which that series is that function. So that gives us an interval of convergence. So the set of values of x for which the series converges is the interval of convergence. And the radius of convergence, maybe we can see this from here, this series here, the radius of convergence is just given to us by this right here, because we're 1 unit this direction and we're 1 unit this direction, right? So that's our radius of convergence. So, you know, it just kind of looks like this. I'm going to write it out. We'll do A here, our center. This interval of convergence is all of this. The radius of convergence, capital R, is just one of these. So actually the radius comes from the absolute value statement. The interval is when you get rid of the absolute value statement.
Wait, I have a question.
Yep.
So if it converged from like 4 to 6, the radius would be 1, right?
Assuming you have a symmetric radius of convergence and you centered it at 5, yeah.
But it could be otherwise.
It could be otherwise, yeah. We'll see symmetric intervals about the center, but yeah, it could be different. So, you know, like you'll come up with a statement like we did here, the absolute value of x has to be less than r, and that tells you what your radius of convergence is just in that statement right there. And then when we write this statement, x is less than r but greater than -r, that gives you the actual interval of convergence. I guess we could be more generic here. Or maybe more specific, I don't know. Interval for the, let me scoot this down. No, I think that's fine. I need to erase this though. So that gives us our interval still with the absolute value statement, and then we would just add a to both sides. So we have a minus r here and a plus r over here. And so that gives us our interval of convergence. When you're looking at this right here, that's explicitly showing you what your radius of convergence is. Is this whatever that number is? So again, what that means is outside of that interval, that whatever series you're looking at isn't that function at all. It's totally different. Okay, do y'all have any questions about that? So remember that absolute convergence implies convergence. That's what we're taking with us when we start testing power series. And the three tests we're using, the geometric we already looked at, that was 1 over 1 minus x as long as the absolute value of x was less than 1. But the other two are the root test and the ratio test. So we'll take a break, but we're going to talk about either one of those tests is applicable. Like, for example, when we see example 1, x to the k over k factorial, hey, there's a factorial, I should use the ratio test, right? The important thing to point out here is that the statements here with both the root and the ratio test, when the root and the ratio test are inconclusive, is when the root or the ratio is equal to 1 or identical to 1. So the way that translates here, remember, inconclusive just means it could converge or it could diverge. So when we come up with this particular interval or radius of convergence, since it could be inconclusive, the test is inconclusive at the endpoints themselves, then we have to always test the endpoints. So this root test and this ratio test will give us the interval, but it's up to us to test the endpoints to whether they're included in the interval of convergence or they're excluded from the interval of convergence. So we'll just put a note here. We have to test the endpoints because the root and ratio tests don't guarantee anything about convergence at the endpoints, simply because they're inconclusive. You'll always see that at the endpoints in that interval, -1 and 1, what these things will look like. So I think it's better perhaps illustrated once we look at a few examples. But that's the idea. You just got to remember that when you test a power series. Remember, a power series is different than a regular series because we have our variable x in there. Like if that were just k to the k over k factorial, you don't have to worry about testing endpoints or doing any of that stuff. But the moment we see a variable in there, performing one of these tests, the root or the ratio test, coming up with an interval, you will always have to test your endpoints. So that's super important. Sometimes, as we'll see, the endpoints are still excluded. Other times, the endpoints get included. Okay. So, any comments on that? It's kind of vague at this point because we haven't looked at examples, but all right, let's take a break and then we'll start these. Okay, so let's see how this actually works. Find the interval and the radius of convergence for x to the k over k factorial. So we're going to use the ratio test for the factorial. Our kth term is just what we have there, x to the k over k factorial. And our a sub k plus 1, x to the k plus 1, over k plus 1 factorial. So our ratio r is the limit at infinity. And we're going to do the absolute value of a sub k plus 1 divided by a sub k, or times the reciprocal of a sub k. And notice, like in, what was it, 10.7, when we looked at this, it just involved k, and k was going from 0 to infinity. So k was always positive there. We didn't necessarily need unless we were doing that to an alternating series. But here, x is a variable, so x could be positive, negative, or 0. So we need to keep the absolute value around the x's here. Things involving k will be positive. We're just going to simplify what we have and then take out what's positive. So we have x to the k times x times k factorial. And on the bottom, we want to write k plus 1 as, k plus 1 factorial as k plus 1 times k factorial over x to the k. So we have the absolute value of all of that stuff. We're going to simplify that. As x over k plus 1. The limit operates on k plus 1, k going to infinity. K is that expression for k is always positive. So we have the limit as k approaches infinity on the absolute value of x times 1 over k plus 1. And so the ratio is the absolute value of x times the limit as k approaches infinity on 1 over k plus 1. And the limit at infinity is equal to 0. So I'm just going to write it out like this for the time being.
Wait, no, music converges. Wait.
And say, all right, now that we've computed the ratio, what has to be true about the ratio for this thing to converge?
X has to be any number.
Yeah. So in general, though,
R has to be less.
yeah, r has to be less than 1 for convergence. And our r is the absolute value of x times 0, right? Which is 0
A constant to the k
for any x value.
over k factorial is 0. Those growth rates.
So since r is 0, r is always less than 1. So what does that mean about convergence then? It does converge for what x values though? For all x values it converges, right? Because no matter what x you put in there, your ratio will always be 0, which is less than 1, which converges.
And that means we don't have to test it.
So this power series converges for all x.
Oh, and see if they're less than.
And that's part of our conclusion anyways. So what would be the interval of convergence? Right, all x values. Interval of convergence. Is all real numbers. And since that would have an infinite radius, the radius of convergence is also infinite. No, yeah, it doesn't matter. That's just going to give us our first term to be 1. Remember, a convergence series converges regardless of whether we shift that index. So even if we started this series at k equals to 1,000, it would still converge. It's not going to converge to the same value or the same thing, but we still have convergence, yeah.
Do you start k at like -2? Or do they have to be positive numbers?
Yeah, so if we start k here at -2, then it's a little bit more complicated because then you have to talk about how do you extend the factorial function to include negative numbers.
So we just won't see that.
Yeah, you can do it, we just won't see it. If anyone's interested in how to extend the factorial to
Tony's not.
into the real number system, then you might check out the gamma function.
G is a special G.
The gamma function is a function that's defined in terms of an integral, of a improper integral.
Class would that be done in?
I don't honestly remember when I first saw that. It was definitely after calculus. It wasn't in differential equations. I don't remember when I first saw that. Beyond the positive integers. So you can actually compute with -2 factorial. You can actually compute 3/4 factorial, but it has to do with this function. Okay. So, you know, like, for instance, what we're saying here is that the sum from k equals 0 to infinity of 2 to the k over k factorial, or negative 1.75 to the k over k factorial, or pi to the k over k factorial. All of those series converge. So we've just proved that that series converges for any input. So for any x you plug into that series, they will all converge. So if only we had this in chapter 10, we might have been able to knock out a lot of series at once. And I think it's worth pointing out, at least at this point, this series
Wait, it's not units.
yeah, we have seen that already, right? That was the fourth Taylor polynomial, the fourth order Taylor polynomial for e to the x. So actually, we could easily show with what we know now that this is e to the x for all x. And that series is e to the x, and we've just shown that it converges for any value of x, or all values of x, rather. But anyhow, we don't really do this till 11.3 when we put 11.2 and 11.1 together. So in 11.3 we'll say, all right, we've got all these tools for power series. Let's look at an infinite Taylor polynomial instead of a finite Taylor polynomial. Write that infinite Taylor polynomial as a series that involves x. Perform one of these tests to see, one, what function it is, and where it converges. So the same problem, find the interval and radius of convergence for the following series. What test would we prefer here, the ratio test or the root test? Root test? Why the root test?
You can just get the k.
Right, yeah, because everything's just raised to the power of k. So we'll do the root test. Where rho is the limit at infinity.
Oh,
kth root of our, absolute value of our term there, negative 1 to the k, x minus 1 to the k, all over 2 to the k. So we could take care of the absolute value, then apply the kth root. But for now, what does the absolute value do to our expression?
Makes it positive. Gets rid of negative 1 to the k.
It gets rid of negative 1 to the k. Because negative 1 to the k is negative and positive and negative and positive. This is the absolute value here, makes it always positive. And we still need to leave that there, right? We've got a quantity involving x. Do we need the absolute value around the 2 to the k? No, 2 to the k is always positive because k goes from 0 to infinity. It's 2 to the 0, 2 to the first, 2 to the second. So we'll note here that the absolute value of negative 1 to the k is equal to 1, and 2 to the k is positive. So we could say it's the kth root of the absolute value of x minus 1, that quantity to the k. Let's just write it like this. The absolute value of x minus 1 to the k, and we're taking the kth root of that over the kth root of 2. Of 2 to the k, sorry. And then that's where the root test helps us. Gets rid of those powers of k. So the limit as k approaches infinity on the absolute value of x minus 1 over 2 is what? The absolute value of x minus 1 over 2. Okay, is everybody all right with that? Our root rho is the absolute value of x minus 1 over 2. Okay, then what has to be true about the root for convergence?
Less than 1.
It has to be less than 1.
But greater than negative 1.
That's for the geometric. Okay, so we have this thing has to be less than 1 for convergence. So that thing is less than 1 when the absolute value of x minus 1 is less than 2. Just multiply 3 by 2. Now we're looking at the radius of convergence. The radius is 2. We'll go ahead and finish this here. And then we've got to get rid of the absolute value to come up with the integral. So that's when x minus 1 is less than 2, but larger than negative 2. Or when x is in between negative 1 and 3. Is that it? Is that all we need to do?
No, you have to test the patterns.
We have to test the endpoints, right? Because remember that row is inconclusive when it's equal to 1, right? So if we have -1 for x, we have -1 minus 1, we have the absolute value of -2 over 2, which is 1, right? So even though this says x has to be larger than 1, it could be that we could include 1. It's just when we put 1 back into our root, it's identical to 1 and the root test is inconclusive. So we have to manually test both of these endpoints. Also, if x is 3, then we see that's 3 minus 1 over 2. The root, again, is equal to 1. So hopefully that's hideous enough for you to remember. When you do this, you have to test the endpoints. The other one we didn't, right? We just came up with 0. There weren't any endpoints to test. And what we mean by test the endpoints is we're testing that series. Does that series converge? If so, for what values? So we mean test the endpoints into the original series that was given. So we're in that series there, we're just going to let x equal to -1, see what kind of series we come up with, and x equal to 3, see what kind of series that produces, and then test both of those series for convergence or divergence. Yeah. So when x equals to -1, our series is sum from 0 to infinity. -1 to the k times x minus 1 to the k all over 2 to the k. So now we're back into a chapter 10 setting.
Wait, what's happening?
We're plugging in x equals to 1 in the original series to test that endpoint.
We don't just put it into this.
No, we're testing that series, so you gotta plug it back into the series. I'm gonna just drop the indices here. So we have, let's just look at it like this. This is -1 to the k, and then we have -2 to the k. All over 2 to the k. We're gonna rewrite -2 to the k as -1 to the k times 2 to the k. Here, let me get this different color. Oh, that's too much. Okay, all over 2 to the k. So what does that turn into? Yeah, 2 to the k over 2 to the k, they divide out. What's -1 to the power of k times -1 to the power of k? Just 1, right? It's always 1. Well, I guess we can see it one more step, I guess. So since they're both to the k, we'll just combine them. -1 times -1 to the k. That's the sum of 1. What do we know about the sum of 1?
It's
What does it mean to, from k equals 0 to infinity of 1?
1, who knows?
Plus, right? It's 1 plus 1 plus 1 plus 1 plus 1. Does that converge or diverge? Yeah, of course that diverges. So since that diverges in our interval of convergence, what do we do for -1? You don't include it, right? It's not a part of convergence. So since this series, when x is -1, diverges, we do not include x equal to -1 in the interval of convergence.
It's 1 I think.
Interval of convergence. Do y'all have any questions on that? When you test your excuse me, when you test your endpoints, you will always have a series that can be tested through means of chapter 10. So now we have to test when x is equal to 3. So that's just -1 times 2 to the k over 2 to the k, which is just the sum of -1 to the k. What do we know about that sum?
It diverges.
It diverges, right? That sum is 1, -1, 1, -1. Diverges. So again, that means that we're excluding, or do not, we'll just say again, keep consistent language here, do not include x equals to 3 in the interval of convergence. So sometimes you end up including both, sometimes you end up including one, sometimes you still end up excluding both. It really depends on the series, what those values are. So you have to remember to test. So the interval of convergence, it was the same as we came up with originally. -1 to 3. As long as we're within that domain, if you will, that particular series converges to something. We didn't come up with the Taylor series for it, so we don't know what function it is, but we know it does converge for those x values. And the radius of convergence is 2. That was from this statement we had at the very beginning. So we can look at that center as being 1, because it's x minus 1.
So the radius of convergence in this case is equal to like the difference in the endpoints over 2?
Yeah.
Is it always like that?
Yeah, symmetric, yeah. The ones that we see, for sure. Doesn't necessarily have to be, though. All right. Are there any questions? So the first one, converged for all x, this converges in a specific interval. We'll look at this third example here too, but this theorem says that you've got, when a power series converges, it's going to converge in one of three ways. One, it's going to converge for all real numbers, like we saw with that first example. Two, it's going to converge for some interval. Three, it converges only at A. It only converges for that one particular x value. So it's one or the other. It's not a combination of two or three. They're mutually exclusive.
Only working at the point.
Do what? No.
The third one.
Yeah, the third one converges only at a point. So here, for example 3, we'll use the ratio test again because of the factorial. So it's the absolute value of the k plus 1 term, k plus 1 factorial, over x to the power of k plus 1 times x to the k over k factorial. Okay, so the stuff in the absolute value simplifies to what? Say that again, x plus 1 over k?
Yeah, over x.
Over x, yeah. So we've got a k plus 1 factorial again. We're going to write that as k plus 1 times k factorial times x to the k, all over x to the k times x to the first times k factorial. So the ratio is the limit as k approaches infinity, the absolute value of k plus 1 over x.
Wait. Question. How do we get k factorial times k to the x to the first?
On this first step,
Yeah.
on the bottom,
Well, how did it go from the k factorial to it
It's
being
it's
multiplication to be
multiplication
division?
and then it's
right, yeah, so this is a sub k plus 1, right? When we say a sub k plus 1 divided by a sub k, all we're really doing is a sub k plus 1 times 1 over a sub k.
Yeah, but why is a sub k plus 1 a fraction in itself?
Oh, I see. Should not be a fraction. I just totally made up an entirely new problem. Keeping you on your toes.
I was a little confused.
As you should have been.
Oh, shoot.
Okay, that's what it should be. This is what this should be. Okay, that's better.
That's what I got. I thought I was really missing something.
Just gonna take the L for this test.
So what do we have? The x is the k factorial, k plus 1 times x. Times x. Let's get that over.
we should go to-
All right, we need to keep the absolute value around x.
Be one of those A terms.
K plus 1 is fine, it's positive. So we see here that the limit turns out to be infinity. For the k plus 1 part, times the absolute value of x. Again, for the time being, we're going to leave the absolute value of x in there because the limit didn't actually affect that absolute value of x. So if you just say that's infinity, it's you're going to be off, right? Because then if you just say that's always infinity, that means the ratio is always larger than 1, which means for any x value it would always diverge, but that's not true because we have, remember this is k approaching infinity, so this is just some number that's getting larger and larger and larger times x, right? So we really have to be careful here and look at it in two different ways. We can say that there's two cases here. One, x can be 0, and if x is 0, what happens? It what? It's always 0, right? Which means the series would converge, right? If x is equal to 0, we'll just write it here, then the sum is 0 if x is 0. So that's the context that we need to apply our conclusion that it's infinity times x. Again, keeping in mind that just means that that particular term, the ratio of successive terms rather, is getting larger and larger. But if x is 0, then it doesn't matter that they're all getting larger and larger, right? Because each term is just 0. So if x is 0 here, this converges. The other case is when x isn't 0. So when x isn't 0, what happens? The subsequent terms, the ratio of subsequent terms is getting larger and larger and larger. Yeah, it would have to diverge. Yeah, if x is not 0, then this sum diverges. Because we could test that one here, but I hope we can see just from our test above that if you just get rid of the x for a moment, we're testing that series and seeing that the ratio is always infinite. So then we have a single case where it converges. And it converges only at that particular location. A single value of x, interval of convergence is 0, and the radius is also 0. I mean, I guess if we say interval of convergence is 0, it's really just this set. So we should say that. More technical, I guess. And so that covers condition 3 in that theorem above. So those first 3 examples, we looked at all 3 conditions. Either it converges on an interval, it converges at a specific value, or it converges for all real numbers. Things like this in example 3 are pretty useless to us as far as what we're using series for. We want things that converge for all real numbers or in a particular interval. Do y'all have any questions on any of these examples? Okay. So we'll look at one more of these, and then we'll talk about a few ways we can combine power series to get new power series. Yeah, combining power series, multiplying them, whatever. So what test do y'all want to use here? The root? The root would be good for the numerator for sure. Do we want to try to mess with the kth root of k to the 1/2? Or sorry, yeah, the kth root of the square root of k. Keeping in mind that k has to go to infinity. I have some weird L'Hopital's rule involved. I mean, we could certainly try.
No, please.
Either test is going to have the same conclusion, so it doesn't really matter. Yeah, it doesn't really matter. It's just which one's going to be a little easier to work with. So let's say the ratio test is a bit easier to use. If that were k to the k on the bottom, then yeah, the root test would be optimal. To the absolute value, maybe we should write out our terms here. The kth plus 1 term, x minus 2 to the power of k plus 1, all over the square root of k plus 1. Times square root of k over x minus 2 to the k. So then one of those x minus 2's drop out, and we have, to the k rather, we have x minus 2 to the first times the square root of k all over the square root of k plus 1. The k again is positive. We don't need the absolute around root k over k plus 1. And we'll go ahead and keep the absolute value on the variable, x minus 2, and put that out in front of the limit, because the limit's not operating on this. Y'all all right with what we've done so far? And what's the limit then as k approaches infinity? 1. Right? If you do infinity over infinity, the thing with like a root over a root, this like a square over a square or a cube over a cube root, L'Hopital's rule is just you end up in this infinite loop. So with a root over a root, you always want to look at it as a single root instead of a root divided by a root. Right, and then in effect what we're doing is that limit is passing under the radical, and then we're just looking at the limit at infinity on this polynomial type thing, leading term over leading term. So that limit is just 1, and that's our ratio. The ratio is the absolute value of x minus 2 times 1. And again, for convergence in the ratio test, the root has to be, or sorry, the ratio rather has to be less than 1 for convergence. Which means that x minus 2 has to be less than 1, but greater than negative 1. Or x less than 3, greater than 1. Okay, are we done?
We're gonna test your endpoint.
Test the endpoints, yep. Make this hideous again. Test the endpoints. That's it's just something that a lot of people miss on exams, and it. Hopefully you don't miss it. You know, you're losing points unnecessarily. Because it's not, you've got all the tools necessary to do this. So when x equals 1 or 3, again, we're putting those values back into the series. X minus 2 to the k over root k. And then once you plug that in, you just got to see what series you're dealing with. That gives us negative 1 to the k over the square root of k. Does that series converge or diverge? Converges? Diverges? How do we know? Yeah, alternating series test. It's an alternating series.
Additional.
Use the alternating series test, which says 1 a sub k plus 1 in relation to a sub k. What has to be true? A sub k plus 1 less than or equal to a sub k, right? Which means that that series is doing what? That condition is testing to make sure that the alternating series is not increasing, getting smaller, yeah. So we're making sure that it's not increasing is another way to look at it, but yeah. And 2, what was the other condition? The limit at infinity has to be 0. For the alternating series, what are we testing? What is our a sub k? Alternating part is thrown out, so we're just testing 1 over root k in the alternating series. So is 1 over the square root of k plus 1 less than 1 over the square root of k? Yeah, because the square root of k plus 1 is larger than the square root of k. And is the limit at infinity 0? Yeah. So we have a convergent alternating series when x is 1. Converges by the alternating series test. So we include x equals 1 in the interval of convergence. So now you start to see all of this stuff come together, and you see why it's not a trivial thing at all. I mean, I don't know, I just look at stuff like this and imagine, like, who the heck came up with this, right? Like, who's sitting around thinking of this stuff and coming up with it? It's insane.
So it converges conditionally, right? Because the absolute value of it doesn't converge?
Yeah, so
Do we care about that when we're testing endpoints?
we don't care. Remember, if we look at a series and then we say, okay, that thing converges, and then we put the absolute value around it, we've got a divergent p-series. So we would say that this series, negative 1 to the k over root k, is a conditionally convergent series. But it doesn't matter to us because we're not talking about the absolute value of that series. When we plug in x equals to 1, we explicitly get that and that alone. All right, and then this sum, we've got 1 to the k over root k, which is just the sum of 1 over root k. So now we've got a p-series with p equal to 1/2, less than 1. This series diverges. So we exclude x equal to 3 from the interval of convergence. We're including one of the endpoints, excluding the other. Does everybody have what they need? You can keep that up for a minute if you, Scroll up. More?
Yeah, I'm trying to get this again.
Okay. Yeah, did you not get it?
So many. My final review card is always to learn install
can't just be stuck here
What do we
forever.
have here? Absolute value less than 1.
The conditioner is.
Okay. Do y'all have any questions about that? Okay, yeah.
Did you find R just one more time?
So that comes from here. As soon as we find the ratio or the root, that absolute value statement that we get, whatever we get right here,
Okay.
like that absolute value statement will give us the radius of convergence.
Okay, thank you.
Because we can look at it as it's, how should I say that? Let me think of a better way to explain to you, but yeah, that's where we get that from. The other one we had like the absolute value of x minus 1 is less than 2.
Yeah.
That radius was 2. So that's where we get that from. Yeah. Like, so if we could like go back to that first page, it might make a little more sense. Some of that scratch we wrote down. Like, so when you have that right there, that is your radius of convergence. And then we expand that out to get the interval.
Gotcha. Yeah, thank
Somebody 3, because finally.
All right, so there's a summary for you if you need it.
Or just.
So I just want to mention this before we take off. Now everybody's ready to leave, so we'll make it quick. The idea of this theorem here, that in some examples that follow, is that we can combine power series. So we've got a convergent power series and multiply it by another convergent power series, or we add 2 convergent power series together, or we compose a power series with a different function. What will those converge to, and what are the conditions of convergence when we start manipulating these power series? So that's, if you want to look at that theorem, we'll try to make some sense of it Tuesday. The 11.4 should go pretty quickly, so we should have time to finish 11.2 and probably 11.3 next class period. And then if we have to talk about 11.4 and review on the same day, we can probably get that done. Okay, so I think we're in good shape considering we missed an entire class. I'll see y'all.